Today, we are solving the problem that's been stopping quantum neural networks from reaching their potential. Here's the crisis. When you try to train a quantum circuit, your gradient vanishes exponentially with every qubit you add. At 20 qubits, your training signal is a million times weaker than at 1 qubit. This is the barren plateau problem, and its biggest obstacle between us and practical quantum machine learning. But we have solutions. Today, we are covering five essential strategies. First, understanding what barren plateaus are and why they are mathematically inevitable in deep quantum circuits. Second, the mathematical deep dive that explains the physics behind vanishing gradients. Next, classical optimization techniques that work when gradients fail completely. Then, quantum aware methods that exploit the unique structure of quantum systems. And last, smart circuit design principles that prevent barren plateaus from occurring in the first place. Now let's discuss about barren plateaus. This isn't just a technical inconvenience. It's a fundamental limitation that emerges from the very nature of quantum mechanics. Here's the mathematical heart of the problem. The variance of our gradients decreases exponentially with the number of qubits. Let me repeat that, exponentially. Not polynomially, not linearly, but exponentially. What does this look like in practice? For a single qubit, your gradients might have reasonable magnitude. Add 5 more, then noticeably smaller. By 10 qubits, they're getting hard to distinguish from noise. At 20 qubits, which is not a large quantum computer by today's standards, your gradients are about a million times smaller than they were for 1 qubit. Think of it in this way. You're trying to navigate to the bottom of the valley, but your compass, the gradient, becomes exponentially less sensitive as the landscape gets larger. Eventually, the needle barely moves no matter which direction you face. You're standing on what appears to be a completely flat ground, even though there might be deep valleys all around you. This phenomena was first rigorously characterized around 2018 by researchers including Jared McLean, and it's fundamentally changed how we think about quantum machine learning. The name barren plateau is quite literal. Vast regions of parameter space where gradients are essentially zero. Let's discuss about why this happens. The physics behind this is actually fascinating. As we make our quantum circuits deeper and more qubits and add more qubits, the quantum states they produce become approximately uniformly distributed over the exponentially large Hilbert space. This sounds good. It means our circuits are highly expressive, but here's the catch. It's very high dimensional spaces, which quantum systems naturally live in. Most points are concentrated around the average. This is called concentration of measure, and it's well-known phenomena in mathematics. The very thing that makes quantum computers powerful makes quantum machine learning difficult. This creates a cruel irony. The very feature that makes quantum computers potentially powerful, their ability to manipulate exponentially large quantum states, is exactly what makes them exponentially difficult to train using gradient based methods. Let's dive deeper into the mathematics to understand why barren plateaus aren't just an unfortunate accident, but an inevitable consequence of how quantum circuits work. The key insight comes from random matrix theory and a beautiful mathematical concept called concentration of measure. When we have a quantum circuit with randomly initialized parameters, which is how we typically start training, the quantum states it produces become distributed according to what's called the Haar measure. The Haar measure is the uniform distribution on the surface of unit sphere in complex space. Now here's where the mathematics get elegant and terrifying at the same time. In very high dimensional spaces, most points on sphere are concentrated around the equator, or more precisely around the average. This means that when we randomly sample quantum states from deep circuits, they all start to look statistically similar. And if all states look similar, then small changes in parameters produce statistically indistinguishable changes in the cost functions. This creates a fundamental trade-off that we can't escape with better algorithms or smarter initialization. Deep circuits can represent much wider variety of functions. They are more expressive, but this expressiveness comes at cost of trainability. Now let's look at this factor depends on? What this polynomial factor depends on? This depends on circuit depth D, observable locality, parameter placement. The exponential factor, this is exponential factor, and this is polynomial corrections. This exponential factor dominates, but polynomial corrections gives us hope. They depend on how we structure our circuit, what observables we measure, and how we place our parameters. This is where smart circuit design can help us fight back against barren plateaus. Here's the bottom line. For circuits with deep scaling linearly with number of qubits, barren plateaus are inevitable. But this is crucial. Circuits with deep scaling as log n can potentially avoid them while remaining universal quantum computers. This gives us concrete design principle to work with. All right, we have diagnosed the problem. Now let's talk solutions. The quantum machine learning community has had to get creative, borrowing techniques from across the optimization landscape to deal with barren plateaus. First approach, gradient free approach. If gradients are unreliable, ignore them completely. Gradient free methods like Nelson-Met simplex search, genetic algorithms, and simulated annealing can navigate flat landscapes by exploring the parameter space more globally rather than following local gradient information. Then Covilla. That's constraint optimization by linear approximation. It has become particularly popular in quantum computing libraries. It's robust to noise, doesn't require gradients, and can handle the constraints that often arise in quantum optimization problems. We can use them in deep barrens and plateaus. But we shouldn't give up on gradients entirely. In shallow circuits or local regions of deeper circuits, gradient information can still be valuable. The key is being smarter about how we use it. Standard Adam optimizer often fails spectacularly in barren plateaus. But with careful learning rate scheduling, adaptive momentum, and sometimes gradient clipping, we can make progress. Natural gradients, which account for geometry of parameter space, can be particularly effective. We can use it when shallow circuits there are and local optimization. Now, moving on to hybrid methods. The most successful approaches in practice often combine multiple strategies. Multi-start optimization runs several optimization trajectories from different random starting points. If the landscape has multiple good regions, this increases our chance of finding one. We have a success rate of 50% in multi-stack versus 0% for single stack. Bayesian hopping is another clever, clever technique that combines local optimization with occasional random jumps. Think of it as giving your optimizer the ability to teleport out of barren regions and try somewhere else. In practice, these methods have dramatically different success rates depending on the problems. Now, classical Adam might succeed 10% of the time on barren plateau problems, while ensemble methods combining multiple approaches can achieve 60 to 80% success rates. Now we get to the really exciting part, optimization techniques specifically designed for quantum systems. These methods don't just treat quantum circuits as black boxes. They leverage our understanding of quantum mechanics to navigate the optimization landscape more effectively. Firstly, let's start with layer-wise training, which has emerged as one of the most promising approaches. The idea is beautifully simple. Instead of optimizing all parameters simultaneously, we train the circuit one layer at a time. Here's the intuition. If a 10-layer circuit gives you a barren plateaus, but a one-layer circuit doesn't, then optimize one layer at once. We fix all the parameters in the previous layers, optimize just the current layer, then move to the next one. Think of it as learning to play a piano. You don't try to master both the hands at start. You practice with the right hand first, then the left hand, then slowly combine them. Layer-based training applies the same principle to quantum circuits. The mathematics works out beautifully. Each optimization step involves fewer parameters, so the effective dimensionality is smaller, and barren plateaus are less severe. Then, initialization section. Initialization strategy turns out to be absolutely critical for quantum circuits. Random initialization, which works reasonably well for quantum uh, classical neural networks, can be disastrous for quantum circuits because it immediately puts you in a barren plateau. Identity initialization is setting all the parameters to zero might seem trivial, but it's actually brilliant. It corresponds to the identity operation, which is known as good starting point. From there, you can gradually add complexity without immediately falling into barren regions. Then correlation section. Here's something to make quantum optimization fundamentally different from classical optimization. Parameters aren't independent. In classical neural networks, the gradients with respect to one weight doesn't directly depend on other weights. But in quantum circuits, entanglement creates correlation between parameters. We can exploit these correlations by computing second order information. The Hessian matrix. This tells us not just how the cost function changes with each parameter, but how it changes when we modify multiple parameters together. Then natural gradient section. Finally, the quantum natural gradients represent perhaps the most sophisticated approach. Instead of following the steepest descent in parameter space, we follow the steepest descent in the space of quantum states themselves. This requires computing the Fisher information matrix, which captures the geometry of quantum state manifold. It's computationally expensive. We need O of p square measurements for p parameters, but it can dramatically improve convergence in case where standard gradients fail. Here, the cost is O of p square circuit evaluation per step, and the benefit can escape barren plateaus. The trade-off is computational overhead versus convergence. This is best for high stakes optimization where circuit evaluations are expensive anyway. The key is insight is that we are not just optimizing parameters, we are navigating through the space of quantum states. And the space has its own intrinsic geometry that we can leverage. Prevention is better than cure, and this principle applies strongly to barren plateaus. Let's explore how we can design quantum circuits that avoid these problems from ground up. The most fundamental design choice is circuit depth. We now have theoretical guidance here. Circuits with deep depth scaling linearly or polynomially with number of qubits will almost certainly suffer from barren plateaus. But circuits with logarithmic depth can potentially avoid them while still being universal quantum computers. Let's say we have n equals to 20 qubits, and linear depth will have 20 layers, which is severe barren plateaus. We don't even need to talk about polynomial. If we take n squared, which will result in 400 layers, this will result in severe barren plateaus. Now let's go to logarithmic. Logarithmic of 20 will give us somewhere around 4. This is potentially trainable. This gives us concrete design principle. Aim for O of log n depth, not linear depth, as you might sacrifice some expressivity, but you can gain trainability. The second crucial design choice is your cost function. Global observables that depend on all qubits simultaneously will give you barren plateaus almost by definition. But local observables, those that can be written as sum of terms involving only few qubits each, maintain trainable gradients. Here's why. If your observables only involves k qubits at a time, then the gradient variance scales with size of local system, not the entire quantum computer. So instead of exponential suppression with n qubits, you get constant gradient regardless of system size. Then we are going to parameter reduction strategies. Parameter reduction is another powerful tool. If we can reduce the number of independent parameters through system symmetry constraints or parameter sharing, we reduce the dimensionality of optimization landscape. And then we are going to hardware efficient section. Finally, hardware efficient match your circuit to actual quantum device. Real quantum computers don't have arbitrary connectivity. They have specific topologies with limited gate sets. By designing circuits that match your hardware, you get two benefits. Fewer parameters because you're not trying to implement gates that require multiple swap operations, and better fidelity because you're using the device native operations. Let's see what are the design checklists. We need depth of O of log n or O of 1. Cost function is sum of local terms, parameters reduced through symmetry, and initialization strategy planned. Circuit matches hardware topology. This circuits, the result will be the circuits which are trainable by design. The key insight is that many barren plateaus problems can be avoided entirely through careful circuit design, rather than trying to optimize our way out of them after the fact. And there you have it, your complete arsenal for conquering barren plateaus in quantum machine learning. We have journeyed from understanding the mathematical inevitability of barren plateaus, those exponentially vanishing gradients that make deep quantum circuits seem untrainable, to discovering that this isn't a dead end, but a challenge with concrete solutions. We explored how classical optimization techniques like Kobila and genetic algorithms can navigate completely flat landscapes when gradients give us nothing. We learned quantum aware methods that exploit entanglement correlations and use techniques like layer wise training to break the optimization problems into manageable pieces. Most importantly, we have discovered that the best defense against barren plateaus is smart design from the start, keeping the circuits shallow using local cost functions and matching our circuits to both hardware and problems.
Like and subscribe for more quantum computing videos.